we have drawn over here. So the rate of accumulation of internal and kinetic energy, we need to consider also the kinetic energy, because the total energy is going to be a sum of internal and kinetic energy taken together. So it's in by convection, out by convection, for whatever heat that you are going to add by conduction to this, and whatever be the work done by the system on the surrounding. Now, whenever we talk about work done, it's going to be against certain forces. So we need to identify what are these forces against whom work is being done by the system on the surrounding. Since it's work done by the system, that's why the negative sign comes, because as a result of work done by the system, its energy content would reduce, and that's the genesis of the minus in front of the work done term. So taken together, this is nothing but, as I have mentioned, it's the first law of thermodynamics for an open system. Any question? Okay. Then we need to identify each of these terms, put them into the equation, which would result in a difference equation, and then we divide both sides by whatever length scale that we have chosen, which is del x, del y, del z, and taking the limit when they approach 0, and what we get is a differential equation, which would be nothing but the energy equation. We have taken care of all such energy terms in there. If the situation warrants, then we could have a heat source term added to the equation. For example, a nuclear or other heat source, if they appear, if they are pertinent to the situation, then that could also be added as an additional term to the right hand side of this equation. So what's the accumulation of internal and kinetic energy, where we define U as the internal energy per unit mass of the fluid, multiply it with rho, so it becomes internal energy per unit volume, and then you take the time derivative of that, so it's rate of internal energy per unit volume. If you remember the Navier-Stokes equation, all terms in Navier-Stokes equation are something per unit volume. So similar to that, here also all terms, energy terms, are expressed in the form of energy, rate of energy per unit volume. So that's why we have this rho multiplied by U, where U is to be expressed as internal energy per unit mass of the fluid, and you multiply it with rho. Similarly, the kinetic energy has also been expressed in this. So the left-hand side of the previous equation, which is the rate of accumulation of internal and kinetic energy, has been expressed in this form. And the presence of this del x, del y, del z tells us that we need to, from the difference equation, if we need to arrive at the governing equation, differential equation, we will have to divide both sides by del x, del y, del z, but that would come later on. So we would now find out what's the rate of convection of internal and kinetic energy. So this is the rate of, this is the internal and the sum of internal and kinetic energy. And then when we multiply it with the velocity in that proper direction, so with the proper component of this, multiply that with the corresponding area, and del y, del z is the area of the x phase. So del y, del z multiplied by Vx times this is nothing but the convective energy coming into the system through the phase at x. Questions? So Vx multiplied by this, that's energy per unit area per unit energy per unit area per unit time, and so then we multiply it with del x, del y, del z, which is the area of the x phase. The one out will have the similar form, except this total, the sum total of the product of these two terms will be evaluated at x plus del x. Then we consider about the y phase having an area del x, del z, and the corresponding component of velocity would simply be Vy, and same for the z phase, where this being the area of the z phase. So the sum of these 6 terms gives us the amount of energy which is coming into the elemental volume del x, del y, del z by convection. And once again, the appearance of Vx, Vy, or Vz explicitly in these terms would signify that they are associated. Then we write the net rate of energy in by conduction, and which is straightforward. This being the heat flux at x, the conductive heat flux at x, multiply that with the area, and similarly the amount out would be the q evaluated at x plus del x. So in a similar fashion, we have for the Qy and for the Qz. So these six terms now tell us the net rate of heat addition to the control volume, to the elemental volume, because of conduction. So we have taken care of conduction, convection, and then conduction. So what remains to be evaluated is what's the work done. Now you could have worked in situations in which work is done against a volumetric force. The volumetric forces are more commonly known as body force. One example, it could be gravity, which is used here for developing the equation. You could have electrostatic, magnetic, or other forces. Only the instead of acceleration due to gravity, you need to add the corresponding term for magnetic and for electrostatic. And there could be also for work to be done against surface forces. Now we are aware that surface forces generally could be of two different types, especially for macro scale systems. They could be against pressure, or there could be viscous forces. So the rate of work done is force times distance by time. So therefore the rate of work done is force times the velocity in the direction of the force. So with this, now we are going to evaluate each of these terms and plug them back in the difference equation to obtain the equation of energy. So let's see what is the work done against gravitational force. So this is this multiplied by Vx, Gy multiplied by Vy, as I have mentioned over here, that force times velocity in the direction of force. So this force per unit mass multiplied by Vx multiplied by Gy multiplied by Vy, and so on. Everything multiplied by rho times the volume. So you know what's the work done against the gravitational force. Questions? Okay. Then we have the pressure. What is the work done against static pressure? So P being the pressure at x multiplied by the velocity component in the x direction multiplied by del y del z tells me what is the pressure force acting on the x face on the x face and on the x plus del x face, and similarly for the y face and for the z face. So the sum of these three gives us the rate of work done against static pressure. The situation gets a bit more complicated when we talk about viscous forces, because unlike the pressure, the shear stress is a tensor. So it has 9 components: xx, xy, xz, and yx, yy, yz. So each of the 9 components of the shear stress tensor is to be multiplied with the corresponding velocity. So here we understand that this acts in the x direction, tau xx. So that's why the corresponding velocity component is Vx. Yx also acts in the shear force but acting in the x direction. So again Vx, Zx multiplied by Vx. So if you look at the first row, the relevant velocity component which is to be multiplied with the specific component of shear stress is Vx. If you go column wise, then you could see this y warrants that the corresponding velocity component would be Vy and the Z would be Vz and so on. So if I consider this X part, the column part, all these are acting on the X face, which has area of delta Y, delta Z. This has area del X, del Z, and this will have area of del X, del Y, and so on. So these 9 additional components, which are forces against viscosity or viscosity generated resistive forces, are to be accounted for, because they essentially
tell us something about what kind of a dissipation we are going to experience when work is done against viscous forces. Any kind of dissipation or dissipate work done against dissipative forces, for example, solid friction, manifests itself by a change in the energy, by a rise in the temperature. So all forces which are related to work against viscosity are together called viscous dissipation. So viscous dissipation is due to the flow. Obviously, if the system that we are considering is a solid, or if there is no motion, then the viscous dissipation term would not be present. And the viscous dissipation terms become extremely important when, if you just think about a Newtonian fluid, so this tau is mu times the velocity gradient in the appropriate direction. So if you expand the velocity gradient, you have a velocity and a length scale, velocity divided by the length scale. So if the velocity is large, then the viscous dissipation could be large. Or if the system size is small, that means the denominator, the length scale x or y, whatever it is small, that could give rise to a large value of velocity gradient. So whenever you have a large value of velocity gradient, because of high velocity or a small length scale, those are the situations in which viscous dissipation cannot be neglected. But for many real life situations, for example, flow of water through a pipe, the velocity gradient is not large and the velocity itself is not too high. So therefore, viscous dissipation need not be considered for such cases, and you would have almost an imperceptible change of temperature when you measure the temperature of water over a 1 meter pipeline, and you wouldn't sense any increase in temperature. But if it is done on a microfluidic scale, when the system length scale is of microns, then even for a small velocity, it could be large and you could sense high viscous dissipation. Or the re-entry of a rocket, the extrusion of a polymer melt, the motion of a hypersonic jet, and so on. All those are associated with high viscous dissipation. So when you plug these into the equation, and here I jump maybe about 10 steps, which is nothing but algebraic manipulation of the terms, expressing it in the form of substantial derivative, which I'm sure you remember. So the substantial derivative is simply del t del time, Vx del t del x, Vy del t del y, and so on. So this is the accumulation term. This is the heat conduction term. This is the expansion effect. And the last one is the viscous dissipation, which I have just described. So once you simplify this equation by saying that rho is not a function of T, the temperature change is not going to result in a large change in the value of rho. So this is slowly coming towards the equation that we are familiar with, and I have also added the condition that there is no viscous dissipation, which is quite common in many situations. Herein I have added the additional term that I have mentioned, that this is just the heat to be generated, heat generated inside the control volume inside the control volume. So Q dot is the amount of energy generated per unit volume due to electrical heating or some other sources. So this is just an additional term which may or may not appear depending on the application that we are talking about. So when we talk about a solid, then the rho and we assume that rho is a constant, and of course there are no velocity components to be considered for the case of a solid. So d dt, that substantial derivative of temperature, would simply becomes del T of temperature. So this is the conduction equation that we are familiar with, that we have used in solving the problem. So starting with the most generalized form of the equation, which is the energy equation, that takes into effect the viscous heat dissipation, the convection, conduction, and energy generation, we could simplify it to situations in which in which there's no heat generation even for a solid, we get back the equation that we are most familiar with. So this is known as the energy equation, and the entire derivation has been provided in Bode, Stewart, and Lightfoot. So if you wish, you can take a look at it in order to see more applications, or how each of these terms are evaluated. But I thought that that's not necessary for this class. Interested students can see the entire derivation in Bode, Stewart, and Lightfoot. So if we recall what we have done so far, starting with the Fourier's law, Newton's law of cooling, equation of energy in Cartesian and cylindrical coordinate systems. So I will write the cylindrical coordinate systems later on. So there are certain terms. This is a reiteration of what I have just said. So this is a transient term. Then we have the convection term. All the velocities are there. Then we have the conduction term, and then we have the viscous dissipation, which is this one, and then we have the generation term. So this together gives us the energy contained of a body at any given instant of time. And this is the most complete description of the thermal energy or the heat transfer, as we know, for any system, be it solid, liquid, or a gas. And you have when you transform the coordinate system, the relation looks a bit more complicated. But if you look at the significances, they still remain the same. The convection on the left hand side, transient on the left hand side, conduction on the right hand side, and other terms which I have already explained. So these are the equation of energy in Cartesian coordinates, cylindrical coordinates, and in spherical coordinates. Any question? Everywhere the significance remains the same. If you superimpose on this the Navier-Stokes equation, the left-hand side of Navier-Stokes equation is always the convective transport of momentum and a transient term, conductive transport of momentum, and the forces which are present. The forces that we have considered in Navier-Stokes equation are the surface forces, surface force pressure, and the body force, which is gravity. Any questions so far? So, this is a very brief description of the energy equation, and this really helps us. Where are we? This will really help us in solving more complex problems in a much more fundamental and general way. So I would solve with you a problem which involves viscous heat generation. So in the viscous heat generation, it's heat conduction with viscous heat source. Now there are two concentric cylinders which are very close to each other. So what I mean to say here is that this gap B is quite small as compared to the radius of the cylinder. One of the cylinder is kept stationary, and in between the two cylinders we have a lubricant. Now, the rotational speed of the outer cylinder, let's say, has been provided to you, and the inner and the outer temperature, which is TB and T naught, they are also specified. What is being asked to you as a chemical engineer is to choose a lubricant for such a system. Now, when you choose a lubricant for a system in which the two cylinders are at two different temperatures, one being kept stationary, the other is being rotated, what would be your considerations? How are you going to approach the problem? Just some idea from your side. Tell me something. Okay, there are a sizable number of students present in here. So who's there? Varun, anything that
So I'm not sure.
you're not sure? Fine. Varun, let's expand it a little bit more, and anyone can jump in at any point of time. The first thing that should come to us is this B is very much B is quite small in comparison to R. So what this allows us is to change the cylindrical system as we have done before to a Cartesian coordinate system. This is what I have drawn over here, that T0 being the temperature, which is, I mean, maybe some T0 is the lesser temperature and TB is the higher temperature, and the situation is essentially a Cartesian coordinate system. One plate stationary, the other plate is moving with a velocity r omega. And if it's just a conduction problem, then the temperature profile would look like this, that it starts at T0 and goes all the way up to TB with a linear change in temperature. So if we agree that is to be the approximation which we can adopt, can anyone else tell us something, that how do I choose the lubricant? You all are aware that a lubricant works best within a certain temperature range. If you go beyond that temperature, whatever be that temperature specified depending on the constituents of it, it will lose its lubrication property, and which is something known as the breakdown of a lubricant. So it will not act as a lubricant, it will degrade. So you have to be very careful about the choice of the lubricant. So now can you answer? Pratik, your view on this? What should be the criteria that you are going to set for the choice of the lubricant? Pratik, any idea? Okay. Who's SR? SR and YG. SR and YG, any one of you?
Sir, I think we should choose the lubricant such that it should sustain. I mean, it should sustain in the temperature range. Temperature range will be the maximum temperature range and the minimum temperature. That should be the criteria for the lubricant. So we need to find the T max.
You need to find the Tmax. Okay, fine. So you have identified part of the problem, that we need to find the Tmax. So any lubricant that we choose, it should not experience that temperature, that Tmax, so-called Tmax, at which it will break down. So fine. So we move to the so we have identified the problem. Now let's go back to this diagram once again. What is the maximum temperature that you can anticipate? And T0 is more than obviously T0 is greater than less than TB. Are you sure that obviously our first inclination would be to choose TB as the maximum temperature, but do you have any doubts in your mind that whether or not TB is going to be the maximum?
Sir, if there is a viscous heat source, then it might possible that the temperature profile may be other, I mean, parabolic or something other. So it might happen that the Tmax would lie in the film of, I mean, liquid film.
Okay. So what you are saying is that the viscous dissipation in this could result in sufficient heat generation in the system such that you would get a curve wherein wherein the maximum temperature may not be TB, and the profile could be something like this, where the temperature over here at some yet to be specified point may exceed TB, right? So
Yes, sir.
this is what you are saying, that there is a possibility, if there is enough viscous heat generation, then the temperature in between the two plates could be more than either of the plates, even the plate with having the higher temperature TB. So this sort of a nonlinear profile may result. Uh, do you do you can you recall something that you have studied in fluid mechanics or momentum transfer where you have seen curves like this?
Pressure-driven system. So,
It's if you do not have any heat generation, viscous heat generation, then what you have in the using the terminology of momentum transfer would be simply Quete's flow, right? The velocity profile would be linear in between the bottom plate and the top plate. If you have a pressure
yes,
gradient imposed on it, then the linear part is going to be disturbed, and you may get a velocity maximum Vmax in between the moving top plate and the stationary bottom plate. So in terms of developmental logic, the uh, pressure gradient or favorable pressure gradient plus Couette flow is similar in concept to two plates having different temperature. One is moving. However, there is an additional source term being present in the intervening fluid, in the intervening liquid in between 1 and 2. Agreed? So that's the corollary between heat and momentum transfer, which you could see. Now you have done this velocity distribution in this case, and which is x by b times v, where v is this velocity, and it's just a linear velocity distribution. If I assume that the relevant property, which is rho in here, is not sufficiently altered by the presence by the variation in temperature from T naught to TB or to Tmax, then the linear profile of velocity will always be followed. Any question? So we have identified that we need to look at the maximum temperature in between the two plates as a function of operating conditions and as a function of property. So the operating condition, the operating condition obviously would be the velocity of the top plate. It is also going to be a function of or rather the geometry of the system, which is going to be this b, the gap between the two plates, and it's going to be a function of the properties of the fluid, the lubricant that you are going to choose, and the relevant properties obviously are going to be mu and rho. So these are the two principal properties which you have to look at, and more importantly, it's this mu which you would like to see how would it behave with temperature, because viscous breakdown is of a lubricant is when suddenly the viscosity drops to a value where it will flow easily and thereby not have any lubrication. It will not impart any lubrication for flow in between the two. So, is there any question on the development of this problem? So we have identified the problem, and what we need to do is now find what is this dissipation, or what is this dissipative force is going to be. So this is the dissipation function. It's a complicated function that has been provided to you, and we need to we need to see where we are in terms of the dissipation function. Now, for most of the situations that we deal with, this last part, it comes from relaxation, which is for fluids which behave in definitely non-Newtonian nature, and this part is generally not considered for our case. We are going to concentrate on the first part itself. So if you consider the first part, which term would be present? Let's go back to the figure over here. So this is the x direction and this is the z direction. So which one? So this is del vx, del x, del vy, del y, del vz, del z, and so on. Okay. So of this, which one you think is going to be predominant? First of all, there is no Vy, so this term would be 0. There is no, there is definitely a Vz, but the Vz is not a function of Z, so this term will also not be present. So which one do you think? So in this case, I have a Vz which is a function of x. So if I go to this, I have a Vz which is a function of x. So which term is going to be present in this? This is del Vx, del x. Vx is not present. Vy is also not present. Vx is not a function of y. Vz is not a function of y. Vy does not exist. This is Vy by dz, so this term will also not be there. Vz dx. What about this term? Someone tried to say something? Okay, so this is the term which will remain in this, and we are not considering these three terms for this case. So these are for complex polymer melts where there is the concept of relaxation time and all, so that part is not considered. So it is of all the dissipation functions that you can, terms in the dissipation function that you can think of, it is this term which is going to remain in the governing equation. So we know we can start with the equation over here. We can start with the equation over here, and this is a steady state problem. So the first term would be 0, no Vx, no Vy. I'm sorry, no Vx, no Vy. Temperature is not a function of Z. So what we have is the last term over here. T is a function of what? T is a function of x. So the first term would be present over here, and one term due to mu times phi v, which we have identified. These two terms are going to remain in the equation of energy. Okay? There is no additional heat generated in there apart from what you have already accounted for in the form of viscous dissipation. So one term in viscous dissipation and one term which refers to conduction in the x direction for the figure which we have drawn. That would constitute my governing equation. So the term that I have found out for this is going to be del Vz del x whole square. That's the term which we have found from here, which is del Vz by del x whole square. That's the term, additional term, which is there in the governing equation. Had it not been there, it would simply be k d2t dx squared to be equal to 0, and the solution of that would result in this linear temperature variation between T0 and TB. But now I have the additional term of mu times dvz dx whole square. So when we consider all of this, the governing equation, once you integrate that, so it is going to be k d to t by dx square is equals minus mu dvz by dx whole square. And I know already from my fluid mechanics background that Vz is simply x by b times v. So when you plug this in here and integrate it twice, what you would obtain with the boundary condition that at x equals 0, that means at the bottom plate, t is equals t0, and at x equals b, that is at the top plate, t is equal to tb. I leave this solution to it. It's a very simple solution. The resultant temperature profile would be tb minus t naught okay, where this Br is a dimensionless group, which is known as the Brinkman number, and Brinkman number is essentially mu v square. When you solve this, it would automatically appear Tb minus T naught. Whenever you derive a solution like this, you should always examine where in the limiting condition it goes back to the solution that you already know. The second term arises because of viscous dissipation. So if viscous dissipation is negligible, then the second term would not be there, and the temperature distribution that you see would simply be the linear variation of temperature which you would expect for conduction only cases where the two end temperatures are known. So this satisfies the limiting form of the solution. And if you look at the Brinkman number carefully, the V square, it's essentially associated with the V square by the if you divide it by length, if you divide it by length over here, and if you divide by length over here, then what is K TB minus T0 by L? What is that? K times Tb minus T0 by L, where L is the separation in between the two plates. So what does the denominator signify? Temperature difference, or rather temperature gradient multiplied by K.
Sir, conductive heat transfer.
Conductive heat transfer. And if due to the presence of an imposed temperature gradient. If you look at the top part, it is the viscous dissipation part. So the Brinkman number is essentially tells you whether the viscous heating is important relative to the conductive heat flow in such a system. So if Brinkman number is small, that would essentially tell you that the denominator is large or the numerator is small, and therefore small values of Brinkman number signify that viscous heating is important in a system. If Brinkman number is very small, you could drop the entire second term and treat it as a conduction only problem. So that part is now clear. So we have right now with us our temperature profile equation for the temperature profile, and I would like you to find out that when do you think there's going to be a maximum in temperature which would be more than TB. Starting with the known value of temperature profile, can you derive at what condition there would be a maxima in the temperature profile that is more than TB? So you start with the profile and tell me the result when the temperature is going to be when the temperature would be maximum, and therefore in order to choose the specific lubricant, TB is not going to be sufficient. You have to solve for this equation. You have to solve for this equation, but I would like you to find out what is that condition. Can you quickly do that and tell me so that I can catch some breath?
So is it B by sorry, sir, B by 2?
Is it bring? What did you say? I didn't catch you. It's what is the condition at which this takes place?
X equals B by 2 is what I'm getting.
Not included in the location, but when you are analyzing this temperature profile, is there a special condition that you are arriving at which you have to consider viscous dissipation, or at which the viscous dissipation is important? What you are talking about is the location of the maximum temperature.
Sir, the condition I'm getting is BR should be very large.
BR should be very large is obvious from the definition of the Brinkman number. So that is true, but there is as an engineer you need to put some value to Brinkman numbers beyond which or above which you have to solve the complete equation. Below that number, you need not consider viscous dissipation at all. The to if you work with this profile, it should give in order to get the maximum temperature in between x equals 0 and x equals b, you could get some number.
So is it 2?
I mean, are you sure? Are you guessing, or you're
So
confident?
I'm not very sure, but I've done some calculation and I got BR should be greater than 2.
BR should be greater than 2. Can you quickly tell us how you have done that?
So I just took the second term should be much larger than the first term and then proceeded.
Okay. You solve it in your own way, but whichever way you think right. But if Brinkman number is greater than 2, that's the condition. And Brinkman number greater than 2 would tell you that there is a maximum temperature at an intermediate position. I'll leave that to all of you to see that this condition appears automatically when you look at when you analyze this equation. And so as a practicing engineer, the first thing you should do is find out what's the velocity, what is the viscosity, what's the thermal conductivity, and what are the end temperatures. Then you calculate the Brinkman number. If Brinkman number is greater than 2, solve the entire equation and to see what's the temperature profile and what is the maximum of the temperature, which would obviously lie at an intermediate position. If Brinkman number is less than 2, forget about this, and you could choose your lubricant based on the higher temperature, which is TB. But if Brinkman number is greater than 2, if you choose your lubricant based on TB only, then there is a serious chance of viscous breakdown, the temperature breakdown of the viscosity of the lubricant. Clear? Any question? So this problem then therefore underscores the utility of energy equation. I would give you the problem for you to practice on. This is the slate. So it's a laminar flow. In a slate, which you probably remember from your fluid mechanics, and we have a flow of a liquid in between. The length of this is L, and this is my coordinate system, where this is X, Z, and Y. And we will assume the width of the plate is W, and obviously the liquid is coming out. So these are the two plates which form the narrow gap in between. So the width is quite, and this is twice B. So the width is very large as compared to 2B. So therefore your Vz is going to be a function of X only. It's not a function of Y, and it's fully developed flow. So it's not a function of either Z or Y because of the geometry that we have described so far. Both plates are at same temperature. Both plates are at temperature T0. So you need to find what is the functional form of temperature. What is the maximum in terms of maximum velocity? So temperature is to be obtained as a function of X with the Vmax present in it. Now you could very well see that at the first impression you would have is that since both the plates are at the same temperature, so the fluid is also going to have the same temperature, and the maximum temperature is going to be the temperature of either one of these two. Okay, like you could also assume that the temperature of the incoming fluid and the incoming fluid over here and the temperatures of the two plates are the same. So 25 degrees centigrade water is flowing in between two plates which are also maintained at 25 degrees centigrade. But it's a problem of where you need to include the viscous heating, and there you would see that the maximum the temperature is going to increase in between the two plates, and therefore the maximum in temperature could very well be at the midpoint in this. So I'll provide the final answer to you to practice on. T minus T0 would be equal to 1/3 mu Vmax square by K times 1 minus X by B to the power 4. So this should be the answer to the problem. Is the description of the problem clear to you, or do you have any question on this? Normally we'll have, can I move on to the next problem?
Yes, sir.
Okay. So normally I would give a break after 1 hour, but today what I intend to do is I would intend to just discuss one more problem and then end the class. So if you permit me, I'll just simply continue for half an hour and then let you go. Is that okay with you, or you want a break right now? Can I continue, or you want a break of 5 minutes? It's up to you.
So you can continue.
Are you? Is there any difference in opinion on this? Okay, so I would continue in for the next problem, and then we'll end the class. This is the problem of transpiration cooling. As the name suggests, that there would be some sort of an evaporation that's going to take place, or some sort of a phase change that it could take place. I'll describe the problem first. We have an inner sphere whose temperature is to be maintained at some very low temperature. We are talking about cryogenic situations. In cryogenic situations, you have an inner core sphere where, let's say, you are storing liquid oxygen. It is to be maintained at a very low temperature. So one way of achieving that is, apart from very good insulation, is to enclose it in a larger sphere which is porous, and the periphery of the inner one is also porous. So what is done is, if the temperature of this liquid oxygen is T kappa, and the air is being flown in here at T kappa, which then exits out through the pores of the inner sphere, and they will then travel the space in between the two spheres, and then they go out through this. There is a refrigeration coil which maintains the temperature of the liquid oxygen as T kappa. So as an engineer, a heat transfer engineer suggests that the load on the refrigeration coil can be reduced significantly if we make a situation like this, where air at that same temperature as that of the liquid is made to flow through the pores of the inner sphere, through the intervening space, reaching the outer sphere, and then going out of it. If we do that, then the load on the refrigeration coil can be reduced significantly. That is what someone has proposed, and it is your job to see that whether it truly reduces the heat to be extracted out by the refrigeration coil in order to maintain the temperature at the inner liquid to be T kappa, Tk. Is my problem statement clear to all of you? Do you have any questions on the description of the problem? Okay. So the outer sphere temperature is T1, and the inner sphere temperature is obviously Tk, and the same as the temperature of the air which is being blown in here. Now, if you consider this problem, first think about the problem. Let's say I do not have airflow in like this. So this is at Tk, and the outer one is at T1, and we have air in between. So since there is no flow, the heat to be extracted by the refrigeration coil must be equal to the heat which comes by conduction through the air to the inner sphere. So since there is no flow, there is no convection, so there is only going to be conduction from the outer sphere to the inner sphere, and whatever heat comes by conduction must be removed by the refrigeration coil, otherwise a phase change of the liquid will take place. What we are providing now is a flow in a direction opposite to that of the conductive flow. So I am creating a convective flow which runs against the conductive flow. So a convective flow of heat which runs counter to the conductive flow of heat, and hoping that would reduce the amount of heat that reaches from the outer sphere to the inner sphere. So if we can reduce that heat, then the load on the refrigeration coil would be less. So this is how we need to tackle the problem and find out how much of heat arrives when you have a counter flow of convective heat, and how do these two compare? Only convection, only conduction, and conduction which is opposed by convection. That is the crux of the problem. Is that clear now?
Yes, sir.
Okay. So now then we could move to this. Let me see if I have. Okay. We could move. We could discuss the problem. First of all, it's a cylindrical system in which V theta, spherical system in which V theta is 0 and V phi is also 0, and therefore the equation of continuity is simply the one where we have the non-zero component of velocity is Vr, that is the radially outward flow of air in the system. So if this is the continuity equation, as we have seen before also, it is advisable sometimes to start with the equation of continuity because it gives me an expression, a functional dependence of Vr on other parameters. And it essentially gives me the variation, how is Vr related to R, the radial direction in the system. And Wr is the mass flow rate of the gas, which is this one, the mass flow rate of gas which is coming in through the small tube and distributed evenly through the inner sphere and goes out. So therefore Wr is the constant radial mass flow rate of the gas, and my velocity, radial velocity, is a function of R, which is the functional dependence is V is inversely proportional to R square. Now comes the equation of energy. So we obviously have to choose the spherical coordinate system. I mean, this is another example of why we need the equation of energy, because the equation of energy is something. Because if you want to solve this problem by making a shell heat balance, it would be almost it would be next to impossible. So we deal with this case starting with the spherical coordinate. How about the first term on the left hand side?
0.
First term would be 0 since we are talking about a steady state problem. The second term, Vr del T del I.
So I think it will survive.
Second will?
It'll survive. It'll stay.
It will remain in the equation. It will survive. Fine. The third term obviously is 0 since V theta is 0. The fourth term is 0 since V phi is 0. How about the first term on the right hand side?
So it'll remain.
It will remain. T is a function of R. T is not a function of theta, so this will disappear. T is not a function of phi, so this would disappear also. What can you say about mu phi V from the description of the problem?
So it should survive.
Let's see. Go back to this equation. So it is a slow flow of air which comes in, leaves, and then reaches the outer sphere, where we did not mention anything about the relative size of R and Kr, kappa R. That means the gap between them could be substantial. Okay. Not like the previous problem where the outer one and the inner one, the gap is extremely, they're very small, they're very close to each other. So I have a slow flow and probably an appreciable distance. With this understanding, what can you say about this viscous dissipation term?
So then I guess we can take it as 0.
And take it to be equal to 0. So the viscous dissipation term would not be there since the flow rate of air is rather small. And nothing has been mentioned about the gap in between the two spheres, so it could be significant. Unless they are very close to each other, there is not going to be any effect of viscous dissipation. Additionally, the variation of velocity Vr, which is obtained from the continuity equation, if the radii I mean, you simply do not have the viscous dissipation because of the slow flow and the gap. And of course, there is nothing, no heat is being generated in the space, in the intervening space between the two. So what we have then is this, the second term on the left-hand side and the first term on the right-hand side for our case. Okay. So this is my governing equation, as I have mentioned, and we could use the equation of continuity to substitute what is VR. And when you do that, your energy equation becomes like this. Okay? This equation is an ordinary differential equation which can be evaluated, and once you integrate, you use the proper boundary conditions that T equals T1 at R equals whatever. At two values of R, the temperatures are known. So it's going to be some sort of an exponential function where the capital R naught is simply this, WR Cp by 4 pi K. So that's the solution of the equation which you are going to get. Now, if you have small values of R naught, that means when the flow rate is really very small, then obviously you could expand the exponential term, and what you get is something like this: 1 by R, 1 by capital R, 1 by kappa R, and 1 by R. Then another simplification you could add, or rather another additional condition you could put in, where R is infinite. That means the outer sphere radius is very large and Kr is finite. The inner sphere, which contains the liquid, is finite. Then you get the temperature variation to be like this. Did you come across this type of temperature variation in the previous class or classes? You yourself found out this kind of a temperature variation. Can you tell me where? I'll go back to this. If R is kappa is finite, but the R is infinite, what does this situation becomes? You have a very slow flow of air, and you also have the outer one being infinite with the temperature being equal to T1. Did you solve this problem before? Isn't it the same that a sphere is in a stagnant medium, stagnant because the flow rate of air is extremely small, in a stagnant medium where the medium is having a constant temperature T1 and this R is infinite? What was the result? You have solved it, and you have told me what is the final result.
So something sort of exponential decay in temperature.
Right, and which interesting revealing information that you did get when you solved the equation? Don't you recall that you got a value of Nusselt number equal to 2 for such a case? So when a sphere is in the transient conduction case, if you recall that we have solved for a case in which this inner sphere is at a constant temperature and it is losing heat and losing heat to a stagnant medium, and asymptotic value of Nusselt number is equal to 2. So when you reduce the value of airflow significantly, make it very small, and make the radius very large, then it's the same problem. So you get a Nusselt number equal to 2 for a situation like this. So this with what we have done would tell us that Nusselt number is going to be equal to 2. But that is not our concern at this moment. So we need to find out what is the heat flow to the inner sphere in the minus r direction. Because the amount of heat to be extracted must be equal to the heat which comes to the inner sphere. So what is the heat that is coming to the inner sphere? It is 4 pi r squared, and the r is kr over here, times qr evaluated at r equals kr. So that's the amount of heat which reaches the inner sphere. And what if we assume Fourier's law to be valid, it should be 4 pi k dt dr at r equals kappa r. So the expression for t as a function of r decides how much heat is to be removed from the inner sphere by the refrigerant. And we would have an idea of the improvement in the refrigeration flux, in the improvement in the refrigeration system heat flux removal requirement by plugging in the expression for T that we have obtained in our previous analysis, which is this. Okay. So with a slow flow of air escaping out of the inner cylinder as well as to the outer cylinder, when you plug that in, this is going to be the expression of heat which is to be removed by the refrigeration system from the inner sphere to maintain it at a constant temperature of Tk. Questions? So we understand why it is now important to start with energy equation, get an expression for the temperature profile, use the temperature profile to know, to calculate, to estimate the heat load on the refrigeration system. Fine, but we need to compare that with whatever be the case of heat removal at zero gas rate. Heat removal at zero gas rate is when R naught is set equal to 0. So if you see over here, well, R naught is this. So if I set WR to be equal to 0, R naught becomes equal to 0, and therefore the rate of heat removal at zero gas rate would simply be equal to 4 pi kr T1 minus Tk by 1 minus kappa. So this is nothing but only Fourier's law imposed Fourier's law conduction only case in a spherical system. So this is the heat to be removed when we do not have any flow out of the system. So that's what is known as transpiration. You blow a you create a small convective flow that opposes the flow of the conductive heat flux, and this is the effectiveness what you are going to get, and this is the definition of phi. And for low values of phi, this epsilon tends to this phi by 2. So this tells us that transpiration can be a truly efficient method by which you can reduce the heat to be removed by the refrigeration system by creating a small amount of convection. So conduction and convection in the same direction, conduction and convection in the reverse direction, they can alter the amount of heat flow, the direction of heat flow. If you recall the chemical reactor problem which we have solved in yesterday's class, there was a preheating of the the reactants which are entering the reaction zone, the preheating was due to a flow of conductive heat in the reverse direction of the convective flow of the reactants into the reactor. So conduction and convection operating in the same direction, conduction and convection operating in the reverse direction can cause an amount of heat flow to the system. And in this specific example of transpiration cooling, it shows that using a small flow of a small convective flow opposed to the conductive heat flow can create substantial reduction in the heat to be removed from the inner sphere. So that is what transpiration cooling is all about. And it is equally important, which we would see later on, when you have simultaneous heat and mass transfer. So let's assume that the inner sphere, apart from being at a lower temperature than the outer sphere, let's consider the inner sphere to be made of naphthalene. So it sublimates. Anything that sublimates from the naphthalene ball will travel by diffusion and will try to reach to the outside. So if you have it's also a heat transfer problem. So a coupled heat and mass transfer problem where transpiration could be employed can be another example of the utility of transpiration. So we will talk about that problem later. So this one I will leave it. I have this is another problem of transpiration cooling, where instead of a spherical system, we have two horizontal plates that are separated by a small distance L. The upper plate temperature is TL, so the temperature over here is TL, while the lower plate is maintained at low temperature, T0, and there is an ideal gas which is being flown. And to reduce the amount of heat, that must be removed from the lower plate, which is at a lower temperature. And it's the same as the previous problem. An ideal gas T0 is blown upward through both plates at a steady rate. So you need to develop an expression for temperature distribution and the amount of heat Q0 that must be removed from the cold plate per unit area as a function of fluid properties. So essentially the same one. I can show you the solution. Or I can leave it at this point. I will give you the final result, so which you would be able to do on your own. So if you just note down the figure, I have the solution, which when I upload it at the end of next day's class, you would get the solution. But if you want to try it, the temperature distribution is going to be T minus TL, TL minus T0 is going to be e to the power y by y0 minus e to the power L by y0 e to the power L by y0 minus 1. And this y0 is equal to K by rho Cp V y. Unlike the previous problem, you can see that Vy doesn't change with y. So whatever you have in here, the same flows through this and leaves. So it's a simplified, rather it's a simpler problem as opposed to the previous problem where we have used spherical coordinates. And the rate of heat removal and the rate of heat removal is Q0. The answer to this would be K TL minus T0 by L pi by e to the power phi minus 1. So if you note it down, you can do it on your own and see if you are getting the same results. I have it solved in the subsequent slides, but it's better if you try this first and then look at the solution. Once again, I bring to your attention is the first part of this, which simply tells you that k times dt dx. It is the law of, it is just the conductive flow of heat in absence of any imposed flow of ideal gas through the porous ones. So the second part of the expression gives you an idea of the effect of transpiration in such a system. So this is e to the power 5 minus 1. So this is for you to try. Any questions so far? So we have established the equation of energy. We have solved for the equation of energy and demonstrated its utility for the case of viscous heat dissipation and for the case of transpiration cooling, two of the important applicative examples of heat transfer that a practicing engineer may be asked to solve. So I will end here today, and if there are any questions, I'll try to answer. Otherwise, we'll meet on our regular class on Wednesday. Is there any question that you may have now? If not, thank you very much. I will meet again. Bye for now.
Thank you, sir.